Hello everyone and welcome to this presentation, which is all to do with quadratic functions and their graphs. We're going to learn about completing the square and how that links with the graph. We're going to look at factorising and how that links with the graph, and we're also going to look at some other aspects as well. So first of all, what I'd like to do is to fill in the gaps please on this table. You can do that obviously on a bit of paper or on a whiteboard if you have it. I'm not so bothered about plotting the graph unless you've got graph paper and you'd like to have a go at that. I will show you what the graph looks like in just a minute, but just find those values, please. Okay, good. And if you have found those values correctly, you should find that they look like that. So we've got that symmetry that we often see with quadratics. This is what the curve looks like. And what we're going to do now is we're going to investigate what happens if you factorize the quadratic and what happens if we complete the square on the quadratic, and we're going to look at how that links in to the actual graph itself. So again, from the work that we did on the last presentation, can you factorize and complete the square on x squared plus 2x minus 8? Please pause the video if you need to, and I'll give some answers out in just a minute. Good. So if you factorize correctly, you should find that it factorizes to x plus 4, x minus 2. And if you've completed the square correctly, then you should find that it completes the square to x plus 1 squared minus 9. Now, if you look carefully at the graph, you will be able to spot, I hope, what the link is between those two forms and the graph itself. So the x-intercepts of that quadratic are the values for which the factorized form has brackets equal to 0. So with the bracket x plus 4 in factorized form, that's linking to the minus 4 on the x-axis as an intercept. And for the x minus 2 in factorized form, that's linking in with the value of 2 on the x-intercept. And we'll look at why that is in more detail later on. Also, completing the square has a very relevant part to play in quadratic graphs, because it will tell us where the minimum point, or sometimes of course it'll be the maximum point, we sometimes call it the stationary point, we sometimes call it the vertex, we sometimes call it the turning point. So there's lots of different names for the minimum point on this curve, but you will notice that the minimum point is at -1, -9. And you can get that value straight from the completed square version. The x value for the vertex, the minimum point, is the value of x that makes the bracket equal to 0, which is -1, and then the value of -9 is as it is. So our minimum point for this quadratic would be -1, -9. Okay, excellent. So this slide here is for your notebooks, please. This is going to form your notes for how to sketch a quadratic. Sketching a quadratic is very different to plotting a quadratic. Plotting a quadratic needs to be very detailed. Every point needs to be in the right place, etc. Whereas sketching the quadratic just needs to show the key features to get all of the marks. And we're going to go through what those key features would be. So first of all, the plan is to find the intercepts with the x and the y-axis. So first of all, if I want to find where the x-intercepts are, then we would make y equal to 0. The reason for that is if you imagine all of those coordinates that lie on the x-axis, every single one of them has a y value of 0. So if we make y equal to 0, that's going to allow us to find any of the x-intercepts. Similarly, if we want to find where the y-intercept is, then we would make x equal to 0. And that's really for the same reason. If you imagine coordinates along the y-axis, every one of those coordinates has an x value of 0. And the great thing about this method is that it doesn't just work for quadratics, it works for any function that you could get at A level. It could be cubics, it could be reciprocal functions, it could be exponential functions. This method will work for all types of graph. Okay, so this slide is going to look at the same quadratic that we looked at for the starter, but we're going to look at it in a little bit more detail and we can also write some notes in our notebook concerning this quadratic in order to get some good notes ready for revision when needed later on. So x squared plus 2x minus 8 is my quadratic, and we've already said that that can factorise to x plus 4, x minus 2, and in completed square form, x plus 1 squared minus 9. So looking at first of all the y-intercept, where the intercept is with the y-axis, we would make x equal to 0. So this is usually fairly straightforward, and in this case you can see here I've substituted x for 0 and I've managed to get an answer of minus 8. So I know that this quadratic is going to pass through the y-axis at minus 8. So I'm going to plot that point first before I do anything else. You'll notice that I haven't put any of the other values on the y-axis. This is because I'm sketching, I'm not plotting. X and Y is labelled. Secondly, I'm going to find where the quadratic passes through the x-axis. We call those the x-intercepts, and to do that I'm going to make y equal to 0. And the factorised form is the easiest way of then determining where the x-intercepts are. So I've made y equal to 0. Here we have the factorised form. I've now got to work out what values of x would make it equal to 0. Well, these two brackets are being multiplied together, so in order to get an answer of 0, either one or both of these brackets has to be 0. So if I make the first bracket equal to 0, that's going to give me an x value of minus 4. And if I make the second bracket equal to 0, then it's going to give me an x value of 2. And that's where the two x-intercepts come from that I'm now going to plot on the graph. Now, although this doesn't have to be perfect, you will notice that the minus 4 and the 2 have been put in relation to each other, so the minus 4 is further away from the origin than the 2. And that's going to help us then to sketch the curve, because it's going to enable me to see where the minimum point is on the quadratic much better by doing those values in the correct place. So here's my sketch. I knew that the minimum point was not going to be at 0 minus 8. So that's a common misconception. Be careful about that. A lot of students assume that the lowest point on this curve is going to be the y-intercept. Because of the symmetry of the curve and the fact that minus 4 is further away from the origin than 2, I know that my minimum point is going to be a little bit to the left of the y-axis. So hence why the graph drops down a little bit further below the minus 8. Minus 8 is not the minimum point. Okay, so we can continue with our notes here, and we're just going to have a look at some key features of any quadratic graph. So quadratic graphs can look like either of these two. The first one is a quadratic graph that has a minimum point, and the second one is a quadratic graph that has a maximum point. And you can see the difference between the two in terms of the equation. The first one has a positive value of x squared at the beginning, and the second one has a negative value of x squared at the beginning, and that creates the two different shaped curves. So this is illustrating again that all quadratic equations have either a minimum point or a maximum point, and on the previous slide I did say that that can be called other things like stationary points, turning points, or the vertex. To find the stationary point, we use the completed square version of the quadratic. So we discussed this on the very first slide, but here is the general rule for completing the square, the general format. We've seen that on a previous presentation, and the stationary point for this particular general quadratic would be at QR. So it's the value of x that makes the bracket equal to 0, as discussed earlier, and the value of r is as it is. The p-value that you're seeing here is just in case you get a quadratic that's, for example, 2x squared or 3x squared, But if you complete the square on that and you get it into this particular form, the value of p can be ignored when you are choosing your minimum or maximum point. It's only the value of x that makes the bracket equal to 0, and the value of r that is important in deciding where the turning point or stationary point, whatever you want to call it, can be found. So we call these curves parabolas, and we can see that they are symmetrical, and the line of symmetry that runs through each of these two quadratics is the equation x equals q. So x equals 2 or x equals 3 or x equals 4, these are all equations that represent vertical straight lines. So while we are on this subject, we will go back to the quadratic that I gave you right at the beginning. Just a reminder, it was x squared plus 2x minus 8. The completed square version of this quadratic is x plus 1 all squared minus 9. And from that completed square form, we can then decide where the minimum point will be. So the value of x that makes this bracket equal to 0 is minus 1. The minus 9 is as it is, and we end up with a minimum point of minus 1, minus 9, which I can now, if I'm asked to, I can place that on the curve as part of my sketch. Sometimes they don't require you to do that. Sometimes they don't require you to find the x-intercepts. It'll be very clear from the question exactly what details you need to give on your sketch. Okay, good. So it's over to you now to practice those skills using these two exercises that you see on pages 19 and 20. We're going to be linking the factorized form with the x-intercepts as we've seen earlier. We're going to be linking the completed square form with the stationary points, a skill that we saw earlier. We're going to be finding the y-intercepts, and ultimately we're going to be sketching those quadratics and showing those key features on those sketches. You may need to look at the previous presentation because we're going to be having to factorize, we're going to be having to complete the square, and we're going to be having to use maybe the quadratic formula. And all of these skills might be on quadratics that have a single x squared, or they might be quadratics that have multiple x squareds. So all of these skills that we've been learning over the past couple of presentations, you're going to need those skills to answer these exercises. Have a go. Any questions, any problems, contact your teacher and they will be able to help you out. Okay, great. So you've practiced those skills by looking at those two exercises. It's time to move on to the final part of this presentation, which is all about the discriminant of a quadratic. And the discriminant is a really powerful tool because it allows us to find out how many roots a quadratic has, how many x-intercepts a quadratic has, before we actually start working on it. So the reason why that's good is that if we have a quadratic that doesn't have any real roots, we might spend a lot of time trying to find them when there is actually none there. So by working out the discriminant, it can save us a lot of time long term. So it's worth doing this right at the beginning of a question. So the discriminant is the b squared minus 4ac part of the quadratic formula. So it's the part that's underneath the square root sign of the quadratic formula, and like I say, it determines how many roots a quadratic has. So if you calculate the discriminant and you find that you get a positive value greater than 0, then what that means graphically is that the quadratic has two unique real roots. We sometimes call them two distinct real roots. In other words, there are two places where it crosses through the x-axis and they are in different places. The next option would be if you calculate the discriminant and it's equal to 0. What that means is that the quadratic has two repeated roots. Now you might argue that it looks as if it has one. In mathematics, we say that there are still two roots, but they are the same as each other, two repeated roots. So you can see that this quadratic comes down, it just touches the x-axis, and then it follows in its usual path. The third and final option is when you work out the discriminant and you find that its value is negative. And what that means graphically is that the quadratic does not pass through the x-axis at all. It has no roots, it has no x-intercepts, and we would just simply say that it has no real roots. And it's important that we state that it's no real roots. Don't just say that it doesn't have any roots. You might also get questions that talk about real roots. Okay, now if a question talks about real roots, then of course these are the two options that it is meaning. Either you're getting two different distinct roots like we're seeing in the first picture, or we're getting equal roots like what you're seeing in the second picture. So if we are dealing with a question that talks about two real roots, then the situation in terms of the discriminant is that it's greater than or equal to 0. So it's combining these two examples in one. Okay, so here is an exercise that we can have a go at in order to decide whether these 6 quadratics that you're seeing in front of you have two unique real roots, whether they have repeated roots, or whether they have no real roots at all. So you'll notice that a lot of them are not in the format that we would normally like to see. The way we would normally like to see these written is like we are seeing in part A. You've got the x squareds first, then you've got the x's, then you've got your number, and then it's equal to 0. So from that we can then say that A is 1 because the coefficient of x squared is 1. We could say that B is 3 because it's the value of the x's is 3, so that's the B value, and C would be -5. And then you could calculate the discriminant from those 3 values and decide how many roots the quadratic has. For the others, you're going to have a play around with them and decide for yourselves what the A, the B and the C value are, and then work out the discriminants and make a decision. So I'll leave you for a few minutes to have a go at that. Pause the PowerPoint, have a go, and then I'll give some answers out after you've had a go. Okay, so in part A, we've already said that A is 1, B is 3, C is -5, and if you place those correctly into the discriminant, you get a value of 29. Positive value, so 2 unique real roots. In number 2, you should have written down that A is 4, B is -3, and C is 7. And if you put those values into the discriminant, you end up with a value of -103. Negative, therefore no real roots. In number 3, be careful because the order is the wrong way around for what we would like, but A is 2, B is 3, and C is -4. So if we put those values into the discriminant, we get 41. So there are 2 unique real roots. In D, we would multiply the brackets out first and bring the 10x across to the right hand side. So A will be 5, B will be -10, and C will be 5. And if we place those values again, we get a value of 0. So 0 represents there being 2 repeated roots. Now in E, I mean, you can either leave these left-hand side terms where they are and bring the 3x across, or you can take the 2 terms on the left-hand side and take them across the right-hand side. It doesn't matter, you'll get the same answer whichever way you do it. I'm going to do it whereby I take the 13 and the -2x² across to the right, and the reason why I'm doing that is so that I'm making my x² positive. I don't have to do that, but it's just something that I prefer to do. So A would be 2, B will be 3, and C will be -13, and if I place them into the discriminant, I get 113. So 2 unique real roots. And then finally, in the last one, we would have to multiply out the brackets and then bring the 2x across to the left-hand side. and we will end up with A being 1, we will end up with B being -4, and we'll end up with C being 5. And if I put those values in, I get -4, which means that there's no real roots. Any problems with them and you're not sure where you're going wrong, again, contact your teacher and they will be able to help you out. Okay, great. So last but by no means least, the last slide is all about what we call a K question. We get a quadratic, but there is an unknown or two unknowns which are called K. It doesn't have to be K, it's just historically that they tend to use K a lot in these types of question. And using the information that we've got in the question, we need to either find the actual values for K, or we need to find the range of values of K for when the condition applies. So let's have a read of this. It says find the range of values of K when the quadratic equation x squared minus 3kx plus 7 minus k equals 0 has repeated roots. And you will be given some information about that quadratic. It might be that it has repeated roots, it might be that it has two distinct roots, it might be that it has no roots at all, or it might be that it has real roots. And we discussed on the previous slide what the discriminant would have to be for each of those cases. So here is how we would set this out. Now we're quite formal with this. This is all for your notebooks. But if you follow this pattern every time, if you follow the steps that I'm going to show you now, then you can be assured that you're going to get all of the marks as long as it's correct. So first of all, we tell the examiner that we understand what we mean by the discriminant if there is this particular condition on the quadratic. So we know that this quadratic has repeated roots, so we know that the discriminant is going to have to equal 0. So you have to write that line down to begin with to get the first mark. If it was two distinct roots, then we would be saying it's greater than 0. If it was that the quadratic had no roots, we'd be saying that it was less than 0. So this line is our setup line, and it's very important. We can now write down the values of our coefficients so that we can place them into the discriminant. So this is where you write down the A value, the B value, and the C value. Now luckily for us, everything's in the right order, so it's not so difficult to decide what those values are going to be. So A is going to be 1 because it's the coefficient before the x squared. B is going to be minus 3k because it's the value before the x. Don't forget that k represents a number, it's not a variable, it's not like x. So it's minus 3k is the value before the x's. And the number on its own, that's the c value, well that's 7 minus k. It's the number at the end of the quadratic that is not attached to any x's at all. So we've got our A, we've got our B, we've got our C. We're now going to place those values very carefully into the discriminant above, and we're going to then determine what the values of K are. So we're now going to work out the discriminant. So this is my condition that I wrote down first. This is me substituting the values for A, B and C that I've just found. Use of brackets is all important. You can never have too many really. It's just to make sure that you don't miss anything out and you don't miss any of the, let's say, the sign clashes. So just be careful with that. Take your time. This is the important bit. If I work through the algebra, and you can do this for yourself, but basically minus 3k all squared is 9k squared. Then we've got minus 4 times 1 times 7, which is minus 28. And we've got minus 4 times 1 times minus k, which is where the plus 4k comes from. Luckily for us, this quadratic factorizes, so that might be a tricky thing to do, especially with it being 9k squared and minus 28. Don't worry too much about that because you'll learn very soon, if not already, that your calculators will factorize and find these values for you. But for now, I can assure you that the factorized version is, as you can see here, And then finally that leads to there being two values of k. The first one is where k is 14/9, which comes from making the first bracket equal to 0, and the second value of k ends up being -2 due to the fact that we've made k plus 2, the second bracket, equal to 0. So what does that mean? Well, what that means is that if I take either of those two k values and substitute them back into the original quadratic, you will end up with a quadratic that has repeated roots. Okay, great. So they're not easy. A lot of them, they can be quite algebraic, and quite a lot of the time we see mistakes made on the manipulation of the algebra. So be very careful with that. Take your time, use lots of lines of working. Don't try and do too much all at once. But to practice that skill, on page 18 of your textbooks, this exercise will allow you to practice a few of those K-type questions that we've just seen. Have a go at them. Any problems, contact your teachers, take photos, send them to your teachers to determine where you've gone wrong, and hopefully by the end of the exercise you're quite confident with that skill. Okay, thanks very much. So that concludes the quadratic graph section. Feel free to do those exercises in your own time, and I will see you for the next presentation.